Hello everyone. Today I will talk about the topic of mid-design of concrete. In this topic, I will talk about the process to find the quantity of the raw materials for use to produce concrete, such as cement, water, coarse, and fine aggregates. In order to meet two requirements, the first one is slump of fresh concrete, and the second one is strength at 28 days. And the process to find the material for using to produce the concrete is suggested by ACI or American Concrete Institute. Before studying the detail to find each materials, we have to know the marginal strength. The marginal strength is the strength that added into the specified composite strength or required strength, in order to make sure that the composite strength of the concrete at 28 days meet the requirements. For the example 1, the required strength at 28 days of this problem is 20 megapascal. And what is the design composite strength of this concrete? In this problem, the required strength of this problem is 20 megapascal. From the table 1, 20 megapascal lower than 21, so the marginal strength of this concrete is 7. The design strength of this problem is required strength or 20 plus marginal strength or 7 megapascal. So the design strength of this concrete at 28 days is 27 megapascal. After we know the required strength and the design strength of the concrete, the next step is to find the quantity of each materials for use to produce the concrete. Before starting to find each material, we have to know the criteria of this problem. The first one is slump of the concrete about 25 to 50 millimeters. And the second one is strength at 28 days about 35 megapascal. In addition to the criteria, we have to know the important basic property of each material. The first one is the density or specific gravity of Portland cement. For the coarse aggregate, the dry compact weight or the unit weight of coarse aggregate in dry condition, specific gravity and water absorption at SSD condition of coarse aggregate. And the last one is the maximum size of coarse aggregate. For fine aggregate, the finite modulus, specific gravity, and water absorption are required. Step number 1, slump of concrete. In the case of the slump of concrete is not given by the problem, we can use the table 2 to set the slump of the fresh concrete depend on the circular member. But in this problem, the slump of fresh concrete is 25 to 50 millimeters, and this concrete used for the reinforced concrete footing. For the table 2, the reinforced concrete footing or the reinforced concrete foundation, the slump of the concrete range between 20 to 80 millimeters. But for the other structure, so you can use table 2 as a guideline to set the slump of fresh concrete. Step 2, the maximum size coarse aggregates is 20. It is given by the problem. And the concrete used in Thailand, the maximum size of the coarse aggregate is typically about 20 millimeters. Step number 3, estimate water and air content. From the table 3, the table 3 divides into two parts. The first part is concrete without air entaining agent, and the second part is a concrete with air entaining agent. In Thailand, Thailand is a hot country, and the concrete used in Thailand is a concrete without air entaining agent. For the air entaining agent is one of the chemical admixture used in the concrete in cold country. From this table, the maximum size of coarse aggregate used in this study is 20 millimeters, and the slab of the fresh concrete is 25 to 50 millimeters. So the water content of this concrete is 185 kilograms per cubic meters, and the air content is 2%. The next step to find the water cementitious material ratio or water to binder ratio. From the table 4, the strength of the concrete is typically depend on the water cement ratio. The lower of the water cement ratio, the higher of the composite strength of the concrete. In this problem, the composite strength is 35 megapascal and the concrete without an intending agent. So the water cement ratio from this table is 0.48. But the table 5 shows the maximum water cement ratio for concrete in sulfate environment. For this problem, the concrete used in this problem is subject to the sulfate attack or in sulfate environment. Means that the table 5 used to find the water cement ratio suggested by ACI. The maximum water cement ratio of this concrete is 0.45. At this step, we have two values of the water cement ratio, 0.45 and 0.48. If we use the 0.48 not meet the requirement of the sulfate environment. So in this problem, we have to use the water cement ratio of 0.45 to meet the strength and the sulfate environment. And the next step, to find the quantity of cement. From the equation, water to binder ratio or the water to cement ratio by weight is 0.45. And we know the water content of this concrete is 185. From this equation, we obtain the quantity of the cement that is 411 kilogram per cubic meters. And at this step, we must keep the volume of the concrete as 1 cubic meter. And from the step number 2, we obtain the air content about 2% and water content of this concrete is 185 and cement content is 411 kilograms per cubic meters. And the last volume is cost and find aggregates. To find the quantity of cost aggregate, from the table 6, the volume of cost aggregate to the volume of the concrete depends on the finite modulus of sand and the maximum size of cost aggregate. In this problem, the finite modulus given by the problem is 2.7 and the maximum size of cost aggregate is 20. So the volume of cost aggregate ratio is 0.63. From the table 6, the volume of cost aggregate is 0.63 and we know the unit weight in dry condition of the cost aggregate is 1,600 kilograms per cubic meters. So we obtain the weight of the cost aggregate in dry condition is 1,008 kilograms per cubic meters. And we know the water absorption of the cost aggregate given by the problem is 1%. So the weight of the cost aggregate in SSD condition is 1,018 kilograms per cubic meters. Step 7. To find the weight of sand. From this diagram, we know the air content, water content, cement content, and cost aggregate content. And the last volume is 5 aggregate. From the ACI, suggests to find the quantity of the sand by using two methods. The first one by keeping the volume of the concrete and the second one by keeping the unit weight of the concrete. But typically, when you order the concrete from the concrete plant, we order in volume. So in this problem, if the volume of the concrete is 1 cubic meters. For the diagram, if we know the weight of the material, we can find the volume of the material. For air content, 2% is 0.02 cubic meters, and the water content 185. The volume of the water is 0.185 cubic meters, and the cement, the weight of cement is 411 kilograms per cubic meter. The volume of cement is 0.13 divided by the density of cement, that is 3.15. And the cost aggregate in SSD condition is 1018 kilograms per cubic meters. The volume of coarse aggregate is 0.377 cubic meters. To keep the volume of the concrete is 1 cubic meter. If we find the total volume of the materials, that is air, water, cement, and cost, we know the less volume is fine aggregate. In the next step, the total volume of the water, cement, air content, and the coarse aggregate is 0.712. Thus, the less volume or the volume of sand is 1 minus 0.712, and the volume of sand is 0.288 cubic meters. The weight of sand, if we know the volume, multiplied by the specific gravity at SSD condition, we obtain the weight of sand in SSD condition, that is 763 kilograms per cubic meters. And the dry weight of sand is 758 kilograms per cubic meters. For keeping the unit weight of the concrete, at this step, we know the weight of the water, the weight of the cement, the weight of coarse aggregate. And from the table 7, the table 7 shows the unit weight of the fresh concrete for different maximum size of coarse aggregate. In this problem, the maximum size of the coarse aggregate is 20 millimeters and concrete without air entaining agent. The unit weight of the fresh concrete of this problem is 2,345 kilograms per cubic meters. We know the total weight of the water, cement, and coarse aggregate is 1,614 kilograms. Thus, the total weight of the sand is 2,345 kilograms minus the total weight of water, cement, and coarse aggregates, that is 731 kilograms for the weight of sand in SSD condition. In this step, for the air content, it has volume but no weight. And this slide shows the summary of the misproportion by keeping the volume of the concrete and by keeping the unit weight of the concrete. It should be noted that the weight of the sand obtained from by keeping the unit weight of the concrete is lower than by keeping the volume. This means that the total volume of the concrete from this column is not 1 cubic meter. As I told you, when we order the concrete, we order in volume, not in weight. So the summary of the misproportion of the concrete is shown in the second column. And use this misproportion to mix the concrete later.